platform, they neither support hot plugging nor the auto discovery of connected devices.
And almost all the on-chip peripherals of an SoC in the embedded world are fixed. So then why would you need a bus interface such as PCI? So you're not going to remove any on-chip peripherals from the SoC like I2C controller, SPI controller, serial port controller. So they are going to be there on the SoC permanently, isn't it? So since everything is permanently embedded, so it doesn't make any sense to implement PCI bus inside an SoC.
And apart from this, the embedded platform also has other bus interfaces like I2C, UART, SPI, SDIO, etc. So all these buses, they don't support hot plugging or device enumeration. Linux gives a common name to all these non-discoverable buses, and that name is platform bus. So from the Linux point of view, all these devices which are non-discoverable are connected to the processor via the platform bus. Linux doesn't care whether it is I2C or it's a HP, APB or L3 interconnect or L4 interconnect. So it doesn't distinguish like that. From the hardware point of view, yes, they are connected to different bus interfaces. But from the Linux point of view, it is just a platform bus, a common terminology used by the Linux. For Linux, it's just platform bus, and the devices which are connected to the platform bus are called as platform devices or non-discoverable devices. All platform devices are non-discoverable. In this diagram, you can say that the I2C controller, what you see inside the SoC, is a platform device. And this I2C controller controls this I2C bus, which has got two I2C devices. Let's say it's the LM75 temperature sensor, and let's say it is RTC devices. Both these devices are also called as platform devices because, for the simple reason, they are not discoverable from their host bus interface. This platform device analogy makes Linux device model design pretty much simple and also avoids lots of code duplications. So to conclude, a platform bus is a pseudo bus. From the Linux design point of view, it is actually a collective name given by the Linux to all passive bus interfaces. And Linux device model considers all these non-discoverable devices are connected to the CPU over this platform bus. Now let's understand what exactly is a device discovery. Let's understand discovery of devices. What exactly is this? Every device has its configuration data and resources, which need to be reported to the OS, which is running on the computer system. An operating system such as Windows or Linux running on the computer can auto-discover these data. Thus, the OS learn about the connected devices automatically. This is what we call as device enumeration. Device enumeration is nothing but it's a process through which the OS can inquire and receive information such as the type of the device, the manufacturer, device configuration, and all the devices connected to a given bus. Once the OS gathers information about a device, it can auto-load the appropriate device. In the PC scenario, everything is automated because of the bus interfaces such as PCI and USB, because they support auto enumeration and hot plugging of devices. However, on embedded system platforms, this may not be the case since most peripherals are connected to the CPU over buses that don't support auto discovery or enumeration of devices. We call them as platform devices, isn't it? And most of the time, since all the on-chip peripherals are already permanently embedded inside the SoC, there is no requirement of hot plugging. That's why the embedded platforms bus interfaces is quite different from the PC scenario. All these platform devices which are non-discoverable by nature, but they must be part of the Linux device model. So the information about these devices must be fed to the Linux kernel manually either at compile time or at boot time of the kernel. Let's see what are those device information. Device information could be many, so here I have listed a couple of points. It could be memory or IO mapped base address and range information. It could be IRQ number on which the device issues interrupt to the processor, device identification information, DMA channel information, device address, pin configuration, power and voltage parameters, and other device specific data. So when you add a platform device to the Linux kernel, you should provide all or some of these information to the Linux kernel so that it can load the appropriate driver, and the driver can extract these information and it can configure the device properly. Let's see how to add platform devices information to the kernel. There are many different ways, but let's discuss two important ways. One is during compilation of the kernel, and second one during kernel boot, that is using a device tree blob. During compilation of the kernel, this is actually a static method. Hardware details are part of kernel files. Kernel files could be board files, drivers, or any setup files. This is actually deprecated and not recommended. Second one is you can load dynamically. That means you can write a small kernel module where you can include all the information about the platform devices, and then you load that module to the kernel so that you can feed all platform device information to the kernel. And the third one is during kernel boot using device tree technique. This is very latest and recommended. In this course, I'm going to cover both a deprecated way as well as the latest device tree way. We are going to see both ways to add the platform devices to the kernel. So what's a board file approach? This method was used before the kernel version 3.7 to add hardware configuration details to the kernel. That is details about the onboard as well as off-board peripherals, fin configuration details. Everything was a part of the board file. You have to recompile the kernel if any device property changes. And all information about hardware configuration was hard-coded in the kernel source files and board files. This was the biggest disadvantage of this board file method. All the hardware configuration of different boards were part of, or they were hard-coded in the Linux kernel source files and in some other set of files. That's why whenever you add any new device, or if you make changes to any device property, then you had to rebuild the whole kernel, reload it, and everything had to be restarted again. That was the problem with this board file approach. That's why the device tree method was introduced in newer kernel versions. The details about the hardware configuration of different boards now lie outside the kernel source files. The device tree was originally created by Open Firmware as a part of the communication method for passing data from Open Firmware to a client program. So the client program in our case is an operating system. An operating system used the device tree to discover the topology of the hardware at runtime, and thereby support a majority of available hardware without hard-coded information. This method avoided hard-coding device information into the kernel source files. So the device tree is actually a text file where you need to follow some syntax to encode the information of your hardware. And later you have to compile that device tree file to create a device tree binary, which the kernel is going to parse it, and it is going to extract the encoded hardware information. Device tree is a method to encode your hardware specific details. If you want to understand more about device tree, then this is a very good place in the kernel documentation. You need to read this document, so from which I have taken this slide information. Don't worry about device tree as of now, because I'm going to cover device tree in this course. And this course also covers writing device trees and using device trees to supply hardware information to the Linux kernel and to your driver. Here I have a Linux kernel source. So the version is little old. It is 3.16. And here you can see that they have used the board file method. Let's go into the SOC specific folder. I'm going to Arch ARM machine OMAP2. And here you can see various board files. There is a board file for BeagleBoard hardware. So there is a board file for Pandora board. There is a board file for TouchBook. This is a board file for DevKit 8000. Now, if you open that board file, you see here all hard-coded FIN configuration details and the platform device information which are hard-coded. And every platform device has its own platform data. Here is a platform data. So everything was hard-coded. After that, this board file calls something called a platform add devices. Whenever the Linux kernel detects a board, let's say the board could be DevKit 8000. Whenever the Linux kernel detects that, the Linux kernel jumps to this function in the board file, where this function then adds all its on-chip as well as off-chip peripherals to the kernel as platform devices. Along with platform devices, the board file also mentions the resources, what it consumes, as well as platform-specific data. If you take a look into the same folder, in newer kernel versions, you see all these board files have been removed. Here is a newer kernel version, 4.14. And if you see the same folder, you can see that there is only one generic board file now. Other platform specific or board specific board files have been removed. If you open this generic and you see now it is pretty much simple, and it supports various boards, and the onboard peripheral details now have been instantiated from the device tree file. You don't see any platform device structure here to represent a platform device. Don't worry, so we'll see more on a device tree little later. We have a separate lecture series for device tree. Let's move forward. In summary, what are platform devices? Devices which are connected to the platform bus are called platform devices. A device, if its parent bus doesn't support enumeration of connected devices, then it becomes a platform device. So you should keep this in mind. What is platform driver? A driver who is in charge of handling a platform device is called a platform driver. In the next lecture, I will see some examples of platform drivers. I will see you in the next lecture. Hey, welcome back to the lecture. Let's see some examples of platform drivers, and I'm going to consider the SoC from Texas Instruments, that is AM335X. This is the main SoC which is being used in our BeagleBone Black hardware. This SoC, here you can see the functional block diagram of this SoC, and you can see that this is powered by ARM Cortex-A8 processor, which can run up to 1 GHz of speed. And this SoC comprises of lots of peripherals, on-chip peripherals, such as it has got LCD controller, inbuilt touchscreen controller, it has got graphics chip, it has got various serial communication controllers or peripherals such as UART. So it has got 6 UARTs, 2 SPI, 3 I2C controllers, and CAN, USB, MacSP, and some of the system related peripherals such as watchdog timer, RTC, memory interfaces for external memory interfacing, and it also supports various parallel data communication peripherals such as MMC, SD, SDIO controller, GPIO controller. All these are actually on-chip peripherals of this SoC, all these are actually considered as platform devices. TI also gives the drivers for all these platform devices. Here I have tabulated for some of the peripherals such as I2C, SPI, USB, CAN, etc. And these are the locations where you can find the drivers for these peripherals. Let me clarify one thing here. The drivers, what you find at these locations, are actually called as controller drivers, or they are actually called as bus drivers. For example, let's say you have the SoC here and you have on-chip I2C peripheral. Now this I2C peripheral is connected to a couple of I2C devices such as temperature sensor, gyroscope, etc. through the I2C bus. In this scenario, these are I2C devices, remember, are also called as I2C clients. And this on-chip I2C peripheral is a controller. It's called as I2C host controller or I2C bus controller or simply I2C controller. Why? Because this peripheral controls the bus transactions on the I2C bus. It initiates the data transfer, it closes the data transfer, like that, isn't it? That's why what you see inside the chip, we call it as a controller. So in this case, we can simply call it as an I2C controller. Whenever someone says I'm writing a I2C device driver, then most probably he's saying he's writing a driver for the I2C device which is connected to the I2C controller over the I2C bus. Basically, he is not referring to writing a driver for the I2C controller. For the on-chip controllers, the driver is most probably it is already given by the vendor itself. That's what this table shows. This is a SPI controller driver which is given by the TI. This is a I2C master mode driver or I2C controller driver. So this is a CAN controller driver. This is a SDIO MMC controller driver. Most of the time, you'll not be writing these controller drivers. As I said, it is already given by the SoC vendor. I hope that clarifies the difference between a device and a controller. A controller always controls the device, and the controller drivers are already available, which is given by the SoC vendor. So in this lecture, let's understand how to register a platform device and a platform driver. First, let's explore registering a platform driver. You just have to use this C macro to register your platform driver with the Linux platform core. The macro name is platform driver register. That's it. You just have to call this macro, and this macro is defined in Linux platform device.h, so you have to include this header file in your platform driver. A platform driver is represented by a structure, struct platform driver. It has a couple of member elements here. Some of them are mandatory to initialize. All this member initialization we will see when we code for our exercise on platform driver. Basically, it has a couple of function pointers to initialize, and it has got the ID table which you need to initialize, and after that you need to initialize some member elements of the device driver structure which is embedded in the struct platform driver. But for the time being, just aware of this structure. This is a structure to represent a platform driver. Similarly, you use platform device register function to register your platform device. This API you can call from your device setup file or from the board file, or you can somehow call this function to register your platform device. Basically, it's a deprecated method, but understanding this method reveals lots of useful information. That's why I will first cover the deprecated one, and later we'll explore the device tree method. a platform device is represented by struct platform device structure. It also has got lots of member elements here, and some are not that important, and some member elements need to be initialized, so which we'll explore when we code for our exercise. Let's explore how a matching between platform device and driver happens. Now you understood how to register a platform device and platform driver with the Linux kernel. You just have to call those APIs such as platform driver register and platform device register. If you just call those APIs, you will register your platform device or platform driver. Now let's attend a very important question. The question is, how does the driver know that you have added exactly the same device which the driver is looking for so that it can configure the device? Or how do you make the correct driver gets auto-loaded whenever you add the new platform device? The answer to this question is due to the matching mechanism of the platform bus core. You already know that a platform driver takes care of a platform device. Whenever you add a platform device, a correct driver has to be auto-loaded to configure that device. That means at the background there should be some kind of matching mechanism. Someone has to match it. A match should be established between a platform device and its corresponding platform driver. That matching is taken care by the Linux kernel itself. You need not to worry about that. You just have to follow some rules while registering a platform device and a driver, so which we'll see later. So this is how the matching works. Let's take the case of a platform bus. The Linux platform implementation or the Linux platform core implementation maintains a platform device and driver list. Whenever you add a new platform device or driver, this list gets updated and matching mechanism triggers. Here, when you add a new platform driver, that driver will get added to the driver list of the platform bus. And when you add a new platform device, that platform device will get added to the device list, which is maintained by the Linux platform core. Remember that every bus type has its match function, so where the device and driver list will be scanned. Let's see an example of matching. There are different types of matching. A simple name-based matching, ID table matching, device tree compatible string matching. But the core concept is same. Let's say there is a platform bus and the platform bus comes with two lists. One is device list and another one is driver list. And let's say there are already 3 platform drivers present in the driver list. So let's say the name of the first driver is XYZ, the name of the second driver is NMO, and the name of the third driver is ABC. When you add a new device to this platform core, what happens? That device will get hooked into the device list of the platform bus and the matching mechanism triggers. So the name of this newly added device is compared with each and every driver of the driver list. And you can see that there is a match. The name of this device matches with name of this driver. That means a match is detected here. So when a match is detected, the bus driver management code of the Linux kernel decides that this is a driver which is in charge of this newly added device. Hence, the probe function of this driver will get called with this device as an argument. The probe function you must implement in your driver. That we'll see later. That's how a simple name-based matching works. Let's take another example. Now let's say there are already 3 devices present in the device list of the platform bus, and there are already 2 drivers present in the driver list of the platform bus. Let's say you add a new driver. When you add a new driver, again the matching mechanism triggers. Now let's say the name of this driver is XYZ, and these are the names of the platform devices. The matching function of the platform bus triggers, and here is a match detected, XYZ, and with this device there is a match detected. So the probe method of this driver will get called with pdev2 as an input argument. That's how a platform driver binds with a platform device. Please remember these points. Whenever a new device or a new driver is added, the matching function of the platform bus runs, and if it finds a matching platform device for a platform driver, the probe function of the match driver will get called. Inside the probe function, the driver configures the detected device. Details of the matched platform device will be passed to the probe function of the match driver so that the driver can extract the platform data and configure it. Basically, while you register your platform driver, you should mention your probe function in this function pointer. So that we'll see when we attempt an exercise. Let's understand what exactly we do inside the probe function of the platform driver. Probe function must be implemented by the platform driver and should be registered during platform driver register. When the bus matching function detects the matching device and driver, the probe function of the driver gets called with the detected platform device as an input argument. And note that probe should in general verify that the specified device hardware actually exists. Sometimes platform setup code can't be sure. The probing can use device resources including clocks and device platform data. So the probe function is responsible for device detection and initialization, allocation of memories for various data structures, mapping I/O memory, registering interrupt handlers, registering device to kernel framework, user level access point creations, etc. All these things you can do inside the probe function. So the probe function may return 0, that indicates success, or error code. If probe function returns a non-zero value, meaning probing of a device has failed. There is one more important function you need to implement inside your platform driver, that is remove function. So remove function gets called when a platform device is removed from the kernel to unbind a device from the driver, or when the kernel no longer uses the platform device. The remove function gets called when a platform device is removed from the kernel. This gets called basically to unbind a device from the driver, or when the kernel no longer uses that platform device, then the remove function gets called. The remove function is responsible for unregistering the device from the kernel framework. Basically, you should be doing some undoing work here of what you have already done in the probe function, like unregistering the device from the kernel framework, freeing memory if allocated on behalf of the device, shutting down of the device, or deinitializing the device. Basically, providing probe and remove are mandatory. You should mention them here. And there are some optional methods you can implement, that is shutdown, suspend, and resume. So the most of the information in this slide has been taken from the kernel documentation, platform.txt. So you should visit this kernel documentation if you need more information. In the next lecture, let's see how to implement a platform driver, and I'll see you in the next lecture. Hey, welcome back to the lecture. So now let's do one code exercise to understand platform devices and platform driver. This will be the implementation of pseudo character driver as platform driver. Repeat the exercise pseudo character driver with multiple devices as a platform driver. The driver should support multiple pseudo character devices as platform devices. Create device files to represent platform devices, and the driver must give open, release, read, write, LSIC methods to deal with the devices. Basically, this exercise will be the implementation of your previous PCD driver as a platform driver. The structure of the driver changes a little bit. So now you have to implement two extra functions. One is probe function and another one is a remove function to handle the platform devices. From the next lecture, let's start implementing this exercise. For the implementation purpose, I will be creating two kernel modules. First kernel module will be our platform driver, and the second kernel module, I call it as a platform device setup. This kernel module will use to add the platform devices. So we'll create two .c files. One is for the platform driver and another one is for platform device setup. What are we going to do in platform device setup? We are going to do two important things. The first one is create two platform devices and initialize them with required information. The required information will be name of the platform device and platform data, ID of the device, release function for the device. And after that, we are going to register platform devices with the Linux kernel. So without further ado, let's get into our editor and let's start coding.
Hey, welcome back to the lecture. So let's start doing this exercise. Now let's create one more project. I call it as 004 PCD platform driver. Here let's create two .c files, one for our platform driver and another one for our platform device setup. I call it as PCD driver, or let me call it as PCD platform driver.c, and another one is PCD device setup.c. First, I'm going to code PCD device setup. So now first let's include some header files here. Include linux module.h, and let's see later whether we need more header files or not. The important thing what we're going to do in this file is we are going to create two platform devices. First thing is create two platform devices. You know that struct platform device represents a platform device. Let's do that. Let's create two instances of a struct platform device. Struct platform device. I call it as platform PCDev1. Let's initialize this platform device. Here you have to initialize a couple of things, but for a time being, let's only initialize the name field of the struct platform device. Let's give one name to the platform device. Later, this name will be used for the device and driver matching. Here, let's initialize the name field is equal to, I give the name sudo char device. For a time being, I'm going to initialize only one member element of this platform device. Let's create one more platform device because we are going to add two platform devices. Name of this device also will be same as before, sudo char device. After that, now let's initialize this ID field as well. This is ID 0. I call it as ID is equal to 0 here. So I have to give comma here. And this will be ID 1. In the group of platform devices, this ID can be used as an index. So this platform PCDev1 at the 0th index. This platform PCDev2 will be at first index. So the ID field can be used for the purpose of indexing. We created two platform devices
And now let's write our modules init and cleanup function. I call it as static int init pcdev platform init. For a time being, let me return 0 here. That is success. And after that, let's implement the cleanup function pcdev platform exit module init pcdev platform init module exit pcdev platform exit. The module description is module which registers platform devices. So that much is sufficient. So after that, let's register our platform device. Here in the module init, we are going to register our platform device. Register platform device. So the API which you are going to use is platform register device. I hope so. Let's search platform device register. You have to call platform device register. Add a platform level device. So you have to pass the pointer to your platform device. Sorry, this is platform device register. The pointer to your device. And after that, let's add another one. Later we'll see how to add all the devices in one go. For a time being, let's stick to this function. This is pcdev2. All these structures like struct platform device and the prototype of these platform device register, everything is in the header file platform device.h. You have to add that header file. I'm going to add hash include linux platform device.h. Whenever you unload the module, so you are going to unregister or remove these platform devices. For that, you are going to use platform device unregister. So now let's compile this code. Let's see what happens. Let me copy the make file from our previous project. The file name will be pcd device setup. Yes, the module builds, no problem. So in the previous exercise, you actually created a structure to represent device private data. In our case, the private data of a device is its buffer information, size, serial number, and permission. In this platform driver exercise, you need to supply all device specific data to the platform driver. That means when you register your platform device, you have to register the device private data also. That's what we call in this context as device platform data. Whether a data becomes a platform data or not, that depends on your project. Let's take an example of permission. The permission, it could be a platform specific data or may not be a platform specific data. That depends on an agreement between a driver and a device. You cannot strictly segregate something is a platform data and something is not a platform data. For this exercise, let's consider the size, serial number, and the permission as platform data. And while registering our platform device, we have to register these information also. And let's do that. Let's create a structure for the platform data. What I'm going to do now here is I'm going to create one header file called platform.h. And here I'm going to create one structure, struct pcdev platform data. And this function comprises of size, another member element to store permission, and a constant char pointer to store the serial number. So these three information will be the platform data of a device in this exercise. I'm going to save this, and let me open our PCD device setup.c. Here let's include the header file platform.h, and after that here let's create platform data. Create two platform data. I call it as 2 here. Struct pcdev platform data. Let's create two instances. So I'm going to create an array. pcdev pdata. I call it as pdata. That stands for platform data. So I create an array of 2 because we have got 2 devices, is equal to. I'm going to initialize the first array element, that is 0th array element, is equal to size of pcdev 0, let's say. So I'm going to choose something as 5112, and next member element is permission, is equal to, let's say, read write, and the serial number, you can save some serial number here. Let me call it pcdev abc1111, something like that, and end this initialization, comma. Let's initialize the next array element, is equal to size. For this I'm going to choose 1024, permission as read write, serial number is equal to pcdev xyz 2222, something like that, and after that let's end this initialization. Now this platform data should be included in your platform device. That's how your platform device is going to supply that data to the driver when the matching happens. Let's again get back to this structure definition to see where we can encode this platform data. Here you can see that you don't have any field to encode that information. Let's go inside this device structure right here. So here is a field to encode the platform data. Platform specific data, that's why you can use this field. What we should be doing now is, let's get back to the code. Here, give comma, you have to dereference the dev field, is equal to. Inside that, there is a field called platform data. Here you should encode the platform data. For this device, I'm going to use the 0th element, pcdev pdata of 0. And for this device, I'm going to use dev is equal to platform data is equal to ampersand pcdev pdata of 1. Let's save and exit. Let's build. That seems to be some problem. Sorry, it is actually platform FORM. Before building this project, let's create a macro that is read write for the permission. I'm going to create that in platform.h and write only 0x10. Let's build, and it compiles, no problem. Complete up to here, and I will see you in the next lecture. So now we have to initialize one more important member element in the platform device. That is, we have to initialize the release function. In the platform device structure, if you just go inside this device structure, this is a big structure actually, and you see a release function here. I think it is somewhere hidden here. Here it is, the release function. This is inside the device structure. This release function has to be initialized. What's a platform device release function? Basically, it's a callback to free the device after all references have gone away. This should be set by the allocator of the device. In your code, you have created the platform devices here globally, isn't it? These are global variables. What if you have created them using some dynamic memory allocation APIs? Then you need a callback whenever you remove that device from the system, because you want a place or you want an entry point where you should release those memories or free those memories. Basically, you need a callback function. For that purpose, release is used. Another example could be here you have used platform data. These are global variables, but what if it is allocated dynamically? That should be cleared or freed once the device is removed. You actually want a callback. That's why you have to initialize the release function. So basically it is in the dev structure. I'm going to initialize here. First, let's do it for the platform device one. Dot release is equal to, I would just call it as PC dev release. So here as well. Let's implement this release function. Somewhere here I would implement that PC dev release. This is a prototype of the release function. So the input argument is pointed to a device structure. Here we are not doing anything, so this is just a dummy function. We are not really doing anything here because we have got nothing to free here. I just print device released. And from my previous exercise, I'm going to copy these macros, which is going to format my output messages. After that, let me just keep some messages here. PR_info module inserted. And I just write here device setup module removed. Let's test this code. Let's build, insert the module. So you can see that device setup module inserted, and let's try to remove this. Sorry. So the insertion and removal is okay. There is no problem. There is no crash detected. That's good. Let's insert once again. And now let's go to sys devices platform, because we have added 2 platform devices. Let's check those entries in this path, sys devices platform. And you see here 2 devices has been registered. It shows 2 entries here. If you remove that, those entries will disappear. You can see that those entries have disappeared. We are successful in adding the platform devices to the system, and in the next lecture, let's write the platform driver, and I will see you in the next lecture. In the previous lecture, you implemented the device setup file, and we tested adding and removing our platform devices. Let's go to the second part of the exercise. Now we should write platform driver. The functionality of a platform driver in this exercise will be same as our previous exercise. It should create device files, it should implement read, write and other methods, and the functionality will be same. The only difference is now we should implement the probe and remove methods, because whenever you load the platform devices and the platform driver, so the matching happens, and if the match is detected, then the probe function will get called. That's why I'm going to copy some code from my previous exercise. First, let's open our file, platform driver. So this is an empty file, and I'm going to copy some code from my earlier project, pcd_end. This is a skeleton code. Here I have init and cleanup functions, and after that this is the file operation structure, which is same, and here are the methods. These methods I'm not going to implement because anyway it will be repetitive, so I will leave that as an assignment to you. Let's just complete these methods. Here just return 0, and for the read I just return 0 here, and for the PCD write I just return no ma'am, and for the open I just return 0 here. Let's continue. So you know that a platform driver is represented by a structure platform driver. Let's create an instance of a structure struct platform driver. I'm going to do that here before this init function. So struct platform driver, call it as PCD platform driver. And now let's initialize some of the member elements of this structure. Here is a platform driver structure. So this structure you can find in platform_device.h. You have to include this header file. We are going to initialize this probe and remove function pointers. And after that, one more important member element we have to initialize, that is inside the device driver structure. Go inside this and you find a name field here. This needs to be initialized with the same value what you have used when registering your platform devices. When the matching code triggers, so the matching code, what it does is it compares the name field of the device driver with the name field of the device. And if there is a successful comparison, then the probe function of our platform driver will get called. Let's get back to the code. Here our first thing is probe. Probe is equal to, our probe function name will be, let's say, PCD platform driver probe, comma, remove function will be PCD platform driver remove. And after that, in the driver structure, we have to initialize the name field. Dot name is equal to sudo char device. I'm going to use the same name what we used in another file. After that, let's end this initialization. And after that, in the init function, we are going to register our driver. For that, I'm going to call platform driver register. Let's search for that function. So the platform driver register, as I explained in the previous slide, this is actually a macro. You just have to pass the pointer to your platform driver here. Ampersand PCD platform driver. Let me just give some message here. Whenever we unload the module, we are going to unregister our driver. That's why I'm going to call here platform driver unregister. And I use the same pointer. Let's implement this probe and remove function. So about this structure, what's the prototype of the probe function? Let's check. This is a prototype. So the return type should be int, and the input argument is a pointer to the detected platform device or matched platform device. Let's use this prototype. Int, this is a name, struct platform device star PDAP. For a time being, let's return 0 and the remove function. So this remove function gets called when the device is removed from the system. This gets called when a matched platform device is found. Let's compile this code. Let's see it builds or not. Before that, let's add some header files here. Since you have used the platform driver structure, so you should be adding here include Linux platform device.h. Let's just edit the make file to add our another file, pcd platform driver.o. That seems to be some problem. So these macros are not defined. For that, I have to include the platform.h. Here, let's include platform.h. Actually, it built fine. There is an issue at line number 112. Let's check that. So this must return integer value here. The module builds fine and complete up to here, and in the next lecture let's add more code to this file. I'll see you in the next lecture. Let's continue coding of our platform driver. What I do is I'm going to keep some prints in the probe and remove function. Here what I'm going to do is I'm going to just write a device is detected, and yes, I'm going to just print this. Let's see how it goes. So here I'm going to print device is removed. And in the device setup, I'm going to change this word to loaded and this as unloaded. Let's build the project. So now both the modules have been built. Let's insert our device setup kernel module. Now let's check the dmessage. You can see that the device setup module is loaded. Let's insert our platform driver module. And here you can see that our driver's probe function has been executed and it has printed a device is detected. But it should print twice because we have registered two devices. I have to check this code again. So we have registered twice, isn't it? That means the probe should get called twice. Yeah, here it is. There is a problem. Here there is a mismatch with the name. This is a matched device because this device name value matches exactly with the driver's name value. That's why this device is detected. But this device is not detected because there is a mismatch in the name. Let's change this. Now it is fine. Let's remove the modules. You can remove in any order. First, let me remove the driver itself. Let me remove the driver. Hit enter and let me run the dmessage. Here it is. When you remove the driver, the remove function was called. That means the kernel is giving you a chance to unbind the device before you unload your driver. That's the reason why that remove function was called. And after that, the driver gets unloaded here. In the remove function, you can do some cleanup activities, which we'll see in this exercise, like freeing a memory. Now the driver is removed. Let's remove our device setup code. Here you can see that when I remove the device setup module, the release function gets called, and after that, the device setup module was unloaded. Let's change the order of module unloading. I'm going to first load driver, PCD platform driver, and let's check the dmessage. Here you can see that there is only one message, PCD platform driver loaded. So it is not showing any probe messages. Let's load the platform devices. That means our device setup module. So now you see a device is detected and device setup module is loaded. Look at this message from where it is coming. It is coming from the probe function. That means as soon as you load this device setup code, the matching code ran and the match was detected, and that's why the probe function gets called here. Let's first remove the device setup code. Let's check the messages. So you have to check these 4 messages here. When you remove your device setup code, so the kernel first called the remove function of the driver. That means the kernel is giving you a chance to free the memory which is occupied by that device before you unload that device from the system. That's why first the remove function gets called. After that, this release method gets called, and after that device was unloaded from the system. Try this at your desk and let me know if you have any questions. In the next lecture, so we will add more code to our project. In the previous lecture, we started coding for our platform driver. Now in this lecture, let's discuss about the data structure, what we're going to use. I'm going to again use this model, device private data structure and driver private data structure. This is something similar to what you saw in the previous exercise, but I have done some minor modifications here. First of all, let's talk about the driver private data structure. It holds some driver specific data like total number of devices it is managing, and I'm going to propose one new member element here, that is device number base, and I use this variable to hold the base of the device number. When I use alloc chardev region, I'm going to use this device num base as an input argument. It actually holds the base of the device numbers. And after that, as usual, you have a class pointer and device pointer here. This will be our device private data structure. Whenever a device is detected or whenever there is a match in the platform device, you know that a probe function will get called. So if there are 10 matched devices, then 10 times your probe function will get called. Each time I'm going to allocate memory dynamically to the device private data structure. This is how the device private data structure looks like. So the first member element is a platform data, because you know that platform device gives you some platform specific data. In our case, it is size, permission, and some device serial number, something like that, right? You need to store that. That's why I'm going to use this pdata variable, struct pcdev platform data, which is defined in platform.h. And after that, this is a pointer to hold the address to the device private buffer. Again, we are going to allocate memory to this buffer dynamically. And after that, this devnum variable stores the real device number of the device. And of course, this is cdev is the next member element which is required for the character device registration. And after that, let's get back to our code, and we have to now code several functions. We have to code our init function, we have to code our cleanup function, and after that we are going to code the probe function and remove function. So I have written comments here to help you understand what we are going to do next. And in this file I also added the device private data structure and driver private data structure. Let's create a variable of our driver private data structure. For the driver, we are going to create one variable globally. But for the device, we will create dynamically whenever our probe function gets called. That makes sense for this exercise. I'm not going to allocate any memory for this as of now. I'm going to create the variables only when a platform device is detected. Let's create a variable for driver data structure. Struct pcdrv private data. I call it as pcdrv underscore data. It's a global variable. First, let's start coding from our init function. The first thing what we do in init function is dynamically allocate a device number for max devices. We are going to maintain one macro here, max devices, and we are going to use alloc chardev region to support max devices. Let's use this alloc chardev region. By the way, I'm taking some code from my earlier project pcd underscore n. Basically, we have to use this alloc chardev region. Let's use that. Remove this variable here, and I call it this macro as max devices. I'm going to keep the same name, pcdev. Here you should give a pointer to store the base of the device number, and for that we are going to use this variable of driver private data structure device num base. Let's use that. pcdrv underscore data dot device num base. Let's create a variable return, and after that, if return fails, then you should quit. Let's copy this code as well. So if return is less than 0, then it's an error. Let's just return here. And after that, the next step is create device class under sysclass. These are one-time creations. That's the reason why I keep them in init function, not in probe function. Probe executes multiple times. We need not to do these things multiple times. So that's why let's create a device class here. pcdrv underscore data class pcd class create pcd class. And if there is any error, then class creation is failed. What you should be doing now is, let me remove this, go to now is, let me remove this, go to, you just have to call unregistered ChArDev region. Let's do that here itself. Here I'm going to use unregistered ChArDev region, PCDRB data, and I'm going to mention the device number base and the max devices macro. Let's create that macro here. Max devices. Let's use 10. And after that, here return the error code. And the third step is register your platform driver. Here we are not doing any error checking for platform driver register. For a time being, I just avoid that. Of course, you should do error checking for platform driver. So if that is negative, then you should undo all these things. That's how we are going to use our init function. And now let's implement the cleanup function. In the cleanup function, first we are going to unregister the platform driver. And after that, destroy the class and unregister device numbers using unregister ChArDev region. We used class destroy and unregistered ChArDev region. The same thing we are going to use here as well. So I'm going to copy these two lines and I'm going to keep that here. Let's do some modification here. This is PCDRB data, device number base, and max devices. That looks good. Let's save this project and let's try to build. Yes, there are no issues with the code and complete up to here, and in the next lecture, let's code for probe. I'll see you in the next lecture. In the previous lecture, we coded for init and cleanup, and now let's code for the probe function. Here I have already written some comments which will help you to understand things better. Whenever the probe function is called, you know that a platform device exists which is relevant to our driver. That's why you should initiate the binding process. That means you should configure it or you should do some work on behalf of that device. First thing what we're going to do is we are going to extract the platform data. If no platform data is available, then you cannot proceed. That's our logic. Some driver may implement differently. If they don't detect platform data, then they may proceed with the default values. In our driver, we will stick to a simple model. So if the platform data is not detected, then we cannot proceed. I'm going to create a pointer variable for our device private data. Struct PCDev private data, a pointer variable. I call it as dev_data. And after that, get the platform data. This is a pointer to the matched device. By using this pointer, you have to extract the platform data. Let's create one temporary variable for our platform data. What is our platform data structure? PCDev platform data. Platform data. I call it as pdata. Let's initialize this pdata is equal to extract the platform data from here. pdev, dereference that, get into dev, and in the dev you have platform data. I actually explained this structure where this structure has this field. So you can extract like this. Or there is already one helper function available in device.h. The name of that function is dev_get platform data. So you can also use this. Let me use this macro, dev get platform data. Instead of this, I just write dev get platform data and I just pass. This actually needs pointer to the device structure. pdev, dereference and select dev. send the address of this. This actually returns a void pointer, so you have to typecast. That's how we are going to extract the platform data. So if this variable is null, then there is no platform data available. Let's check for the null case. Not of p data. Then let's just print that no platform data available. I'll just store the error code in the variable return -e invalid, and I use the goto to jump to the label out. Let me implement out somewhere here. Out. I'm just going to print here device probe failed. Return red. I'm going to maintain one variable return here. That makes sense. Now, if the control comes to the second line, then there was a platform data. So if the platform data is really available, then we are going to extract the data and store it in our device private data. We should allocate memory for this now. And for that, we are going to explore some dynamic kernel memory allocation APIs.
So now let's explore about kernel's dynamic memory allocation APIs. When you're writing drivers or any kernel functions, if you want to allocate any memory in kernel space, then you can make use of this dynamic memory allocation APIs. The important one is kmalloc, where the letter K signifies the memory allocation is in the kernel space. Let's explore more about this function, kmalloc. So the kmalloc is defined in linuxlab.h. If you are going to use this function, then you have to include linuxlab.h. This kmalloc is used to allocate memory in kernel space by drivers and kernel functions. Memory obtained by this function will be physically contiguous. Now let's see how to use this kernel function. You just have to pass two arguments here. First one is size. From the kernel documentation, so this is what mentioned in the kernel documentation about size. The maximum size of a chunk that can be allocated with kmalloc is limited. The actual limit depends on the hardware and the kernel configuration. But it is good practice to use kmalloc for objects smaller than page size. So the page size for the ARM architecture will be 4 kilobytes. That is 4096 bytes. That's why it is always better to limit this size smaller than the page size. And after that, this parameter, that is flags. Flags actually, they change the behavior of the underlying memory allocator. Basically, kmalloc uses something called slab allocator, and by using this flag, you can change the behavior of the memory allocator. Let's explore about these flags in a moment. Now let's see what it returns. This returns null if the allocation fails. On success, virtual address of the first page allocated. The virtual address of the first physical page allocated. Let's explore about some of the flags here. Now this I have taken from the slab.h. Here you can see that kmalloc is the normal method for allocating memory for objects smaller than page size in the kernel. These are the flags which you can use while using kmalloc. Here the very important flags are GFP kernel and GFP atomic. So where GFP stands for get free pages. By using these flags, you can change the behavior of the underlying memory allocator. For example, the most commonly used flag for the process context is GFP kernel. It actually makes the underlying allocator to allocate the memory from the normal kernel RAM. And if the memory is not available at the time your driver requests for memory, then the kernel may put your process to sleep. That means a kernel can put your process into blocked state. That's why kmalloc with a flag GFP kernel may sleep. You should remember this. And when memory becomes available, your process gets unblocked. So GFP atomic flag is another important flag which you can use with kmalloc when you use kmalloc inside an interrupt handler. Because if the memory is not available, then the allocator immediately returns. The caller will not be put into sleep because interrupt handlers cannot sleep. They can't be rescheduled like your normal processes. So most probably you'll be using GFP kernel in your driver when you want to allocate memory dynamically on behalf of process context, and use GFP atomic to request memory from the interrupt handler. So the usage of kmalloc is very simple. Let's say I want to allocate memory for this structure. I just create one structure variable of pointer type, and after that just use kmalloc with size information and the flag, and you have to check the returned pointer. Sometimes it could be null. That's why if it is null, then you can return the error code eNoMem. So now let's see kfree. Kfree is used to deallocate the previously allocated memory. You just have to mention the pointer here. A pointer returned by kmalloc. If this pointer is null, no operation is performed. If you pass null here, then no operation is performed. So don't free memory not originally allocated by the kmalloc, or you will be run into trouble. So use only that pointer here which is previously allocated by the kmalloc. So now there are other flavors of kmalloc like kcalloc, kzalloc, krealloc, kmalloc_array. I would like to discuss one of the most important one, that is kzalloc. Let's explore about kzalloc because kzalloc is preferred over kmalloc. Let's see what kzalloc does. The prototype is exactly same as kmalloc. The only thing what it does is, after allocating the memory is set to 0. It may look trivial, but that is actually a very important thing what this function does. That's why in all your driver code, use kzalloc instead of kmalloc. Then why should we care about memory getting initialized to 0 by the kzalloc? So let's see one use case here. Let's say you have a structure bar, and it has got 3 member elements here, and you create a pointer variable here. After that, you allocate the memory for that pointer using kmalloc. After that, now the memory is allocated, and after that you send that pointer to this function, bar processing function. So it could be some unknown function to you. You just send the argument p bar. Let's say this function is not implemented by you. Let's see what this function does. First, what this function does is it checks this name member element of this structure. If this name is null, then only this function allocates memory for this pointer. So if this name is not null, then this function assumes that you have already allocated a memory for this variable. That's why memory for name is already allocated, so this function doesn't allocate any memory. And after that, what this function does here is it tries to do some memcopy or something where this pointer will be dereferenced. This code may crash if a p bar of name is not a valid pointer. This function doesn't check whether this has a valid pointer or not. It just tries to dereference. Now you may face such issues if you use kmalloc here. Why? Because kmalloc doesn't return a zeroed memory. That's why this variable may be having some random values, and that random value is checked here. If the random value is present, this function assumes that the memory for the name variable is already allocated. It just tries to dereference that blindly, and that could be a crash. So one thing what you can do here is, before sending this variable to this function here, you can zero out each and every member element of this pointer variable. That could solve the problem. Otherwise, just use kzalloc. instead of kmalloc. So it anyway zeroes out the memory locations. After that, kz free. So if you have allocated memory using kzalloc, then you can free that memory using kz free, or you can also use k free, no problem. So only thing is, it is just like k free, but it zeroes out the memory. Let's move forward, and the next one is k-realloc. So k-realloc is used to reallocate the already allocated memory. So the already allocated memory using kmalloc or kzalloc, that pointer you should mention here, and the new size you have to mention here. And this is the same flag which we saw with kmalloc. The use case of k-realloc is, let's say by using kmalloc you have already requested for 100 bytes and now you want to extend it to 150 bytes. Then you can mention that old pointer here, and let's say you want to realloc that to 150 bytes. So you mention the new size here, 150 bytes. So a new pointer will be given to you by this function, and the contents will remain unchanged. The content of the old pointer will remain unchanged. That's about kzalloc, kmalloc, and k-realloc. And now let's get back to our lecture. Let's continue. Now let's allocate the memory for dev data is equal to, I'm going to use kzalloc, and you have to mention the size and the flag, that is GFP kernel. What's the size? Size of this structure. Struct PC dev private data GFP kernel. Or you can simply write like this. Instead of writing this long name, you just write star of dev data. After that, let's do null check, and ret is equal to -e no mem, and let's go to out. That makes sense. Let's proceed to the next step. If the memory allocation is successful, then just copy data from platform data. Let's do that. Dev underscore data, dereference that, and select p data of size. First, let's extract the size information, which is there in this p data. Or you can also use a mem copy, p data of size. P data of serial number is equal to p data of serial number. After that, let's just print these information. I'm going to use a couple of print statements here. So I just printed all these informations of the matched platform device. Our next step is dynamically allocate a memory for the device buffer using the size information what you extracted from the platform data. Before that, let's see whether this code compiles or not. There seems to be some problem. kzalloc, you have to select the appropriate header file for this. This is in linuxlab.h. Let's include that header file. Let's compile. That seems to be okay. Complete up to here, and in the next lecture I'm going to cover these steps, but see if you can able to implement these things. The third step is you just have to allocate memory for the buffer and get the device number. That means you have to now use the device number field of this dev data to store the device number. So you already know the base, and you just add the ID field of the platform device structure. You get the device number. So see if you can able to do this. And after that, do cdev init and cdev add. You already know this because you have already done in the previous exercise. Create device file and handle the appropriate errors. I'll see you in the next lecture. So now let's do the third step, dynamically allocate memory for the device buffer. I'm going to reuse this code.
I'm going to copy that, and here dev data of buffer. So size of, you need not to use size of now because you have the size information, this field. Let's copy and paste that, and this is a flag. If it is not available, and this is a null check, cannot allocate memory, and now you should free this memory. I call it as dev data free. Jump to dev data free and go to dev data free here, dev data free, and you have to use kfree. So dev data. After that, get the device number. That means we have to initialize the dev num field of this device private data structure. This is equal to get the base number from the driver data structure. pcdrv underscore data dot dev num base we have. For that, you do a plus and use the ID field of pdev. Remember, when we are feeding the platform device, we used to use the ID field. That's why that ID field is important. Use that field here, pdev of ID. For the first device, ID field will be 0. So for the next device, it will be 1. That's our device number. After that, do cdev init and cdev add. This is very simple. Now let's get the code from our previous exercise for this. Let's paste here. Here this fops field will be same. All you need to change is this one. Dev data of cdev. You have to pass the address of that. Very simple. cdev init is over. Now let's do cdev add. For the cdev add, so we used to do this. Let's copy this code. Basically, you have to initialize the owner field of the cdev. Dev data of cdev owner field, this module, return is equal to cdev add. Here you should pass the address of cdev, that is dev data of cdev, and here you should pass the device number. Device number is this one, dev num. Let's do that, dev underscore data dev num, and you are going to add one device. That's correct. So the final argument will be 1. If return is less than 0, cdev add failed, and you should clean up the memory for the buffer free. Let's implement the buffer free kfree dev data of buffer. After that, our next step is create device file for the detected platform device. Here you have to take device pcd, which is there in pcdrv underscore data, and device create pcdrv underscore data class pcd. That's correct. Null. Here you have to give the device number. Let's give that dev underscore num dev underscore data. Null and pcdev, this will be same. Here it will be ID, so you have to use the ID field here, pdev ID. You have to check using iserror pcdrv data device pcd device create failed, and you have to do cdev delete here, cdev delete. Let's do the cdev delete, cdev underscore delete. Cdev delete, you have to pass the address of the cdev, dev underscore data, dereference that, select cdev. So if the device create is successful, then we conclude that the probe was successful. I'm just going to print the probe was successful. So at the beginning, let's print one more message here. A device is detected. something like that. The probe was successful, otherwise device probe failed. And after that we just return 0 here. So now let's build it. There seems to be some problem at the line number 162. It should be device numbers. Let's fix that. 162 device. We coded for the probe function and try to finish up to here, and I will see you in the next lecture. In this lecture, let's implement the remove function. As you already know, the remove function will get called when the device is removed from the system. So when the platform device is removed from the system, or when the driver is removed, then this remove function should be used to clean up the memory held by the platform devices. In our case, every device holds 2 memories. You see, in the probe, dynamically we allocate 2 memories, one for the device private data structure and another one for the device buffer. When the platform device is getting removed, then why do you need that memories? We must clear it. That's what we do inside the remove function. In the remove function, you actually get the pointer to the platform device which is going to be removed and use that pointer to clean up things. Now the problem is, how do you access this device private data pointer here? Because this is a local variable. How do you access this pointer here? Because only if you know this pointer, then you can clean up the memory and access any other member elements of the device private data structure. That's why you should find out a way to access this pointer here. That we can do by again using this platform device structure. Let's once again explore this structure. So here is the structure, and here go to device structure, and you see a field here, driver data. You can use this field to pass information from probe to remove. This field is a driver data field which you can set and get with these helper functions. Dev set driver data, dev get driver data. Dev set driver data we have to use in the probe function, and dev get driver data we can use in the remove function. What I'm going to do now is I'm going back to the probe function, and I'm going to save this pointer dev underscore data in the device structures driver data field, pdev. So let's access this pointer pdev of dev. So if you are confused, pdev of dev dot driver data. You can use something like this, is equal to dev data. I'm just saving this pointer in driver data field, or instead of doing this, you can simply use the helper functions provided, that is set driver data. Let's explore this. Here it is, set driver data. You just have to pass the pointer to your data. Let's use set driver data. This takes address to the dev structure, pdev of dev, and your data is dev data. Save the device private data pointer in platform device structure. When you reach remove, you can extract that. So in the remove function, the first thing what we do is remove a device that was created with device create. Let's go to our previous exercise. We used to do this device destroy. This we have to do now, device destroy. Let's do the device destroy. Device destroy, this is class PCD, and here you should use the device number. How do you access the device number? From the device private data structure. How do you get the device private data structure? Let's create one pointer variable to our device private data structure. You should now use a device get driver data. This must be device get driver data. Here it is, device get driver data. You should pass the pointer to the device structure. pdev of dev. And now by using this dev data, get the device number. And the next step is remove cdev entry from the system. The cdev cleanup you have to do. And free the memory held by the device. Device holds two memories. First, clean up the memory for the buffer. Kfree dev underscore data of buffer. Finally, kfree dev underscore data. So all these three steps you have to do whenever you want to remove a device, when the device is being removed. After that, in the probe function, let's use the total devices member element of the driver data structure to count how many devices being probed. At the end here, I'm going to increment the total devices variable, pcdrv underscore data total devices plus I'm going to do here, and I'm going to do minus here. All right, so the build was fine and complete up to here, and let me know if you have any questions. I will see you in the next lecture. In this lecture, let's do some testing. First, let's build the project. The build was fine. And before testing, let me remove any previously loaded kernel modules. Please remove them if you have any. You can always run lsmod command to see all the modules which are currently loaded. This actually lists all the kernel modules. First, let's load the device setup kernel module, or you can even load the platform driver module. So the order doesn't matter actually. Let me first load device setup.ko. So the load was fine, and you can see that device setup module loaded. And now let's load our driver. Let's run dmesg, and here it is. The probe was called. These are all the messages printed by our probe because of the matched platform devices. This was the first match. The serial number is this one. Size, permission, which is printed in decimal, and this was the second device which is detected. So the probe was successful. Let's remove the device setup module. What do you expect when you remove a device setup? So you are going to unregister the platform devices. The remove method should get called in our driver. Let's see. Hit enter, run dmesg. And here it is. The remove function was called, a device is removed, and the release function was called here, and after that another device is removed and device setup module is unloaded. If you do lsmod, you can see that is our platform driver is still hooked up and it is used by none. Let's remove our platform driver. Remove, and the driver is unloaded. No problem, no crash, everything was fine. So now both the drivers have been unloaded, and now let's try to load the platform driver first. So I'm going to load the platform driver first. dmesg pcd platform driver loaded, and now let's try to load the device setup kernel module. Here it is. the probe was called and the details got printed. And now let's first remove the driver itself. I'm going to remove the driver. If you just see here, you can see that both drivers are present. I'm going to remove this driver. So when you remove the driver, what would you expect? You should expect the remove function getting called, because the driver is going away, and before going away it should clean up the devices. Let's remove the driver. Here it is. You can see that the remove function was executed here twice and the devices have been removed here. Then PCD platform driver unloaded. Now let's remove the device setup. Driver is not present now. The driver has already unloaded. Now you are going to remove the platform devices. What do you expect? Do you expect remove function to be called? No, right? Because the driver is not present. The platform core handles everything internally. But in this case, only release function will get called. Here it is. In this release function, you can clean up any platform specific things, like you can deallocate if you have allocated any memory for the platform data or something like that. We didn't face any crashes here. If you find any crash while loading or unloading drivers or during probe execution, something like that, you first have to fix that problem, and then you may have to reboot your machine before loading the driver again. So that's it for this lecture, and in the next lecture let's improve our code to add more features. We completed probe and remove functions, and also we completed init and cleanup functions. I will leave other driver methods such as openread, lseek, release. So those methods you should implement now. I don't think it will be difficult because we have already implemented twice in the previous exercises. I hope you can do that. And if you need any help, then the whole code is present in our repository. Please take the reference from that. In the next lecture, let's explore some more APIs about managing platform devices and resources. And I'll see you in the next lecture.
Hey, welcome back to the lecture. In this lecture, let's explore about resource managed kernel APIs. So now what's the importance of resource managed APIs? Let's take one use case. In your previous exercise on platform driver, you used kmalloc to acquire the kernel memory. What kmalloc does, it actually allocates the resource. The resource in this case is kernel memory. And there is one more flavor of kmalloc that is called devm underscore kmalloc. Now the difference between these two is this allocates a resource. So here this also allocates a resource, but this actually remembers what has been allocated. That's why it is called as resource managed API. Now let's see this further. It is very interesting actually. Whenever you are dealing with a device, so a device is nothing but anything which can be represented by an instance of struct device. You are dealing with a platform device. A platform device can be represented by a platform device structure which actually embeds struct device in it. That means basically in your probe function you are dealing with struct device and you are allocating memory on behalf of an instance of struct device. When you are allocating some memory on behalf of struct device instance, and when you use kmalloc, then it is actually inefficient, because when you use kmalloc, then when this device is getting removed from the system, or when the driver which is managing this device getting removed from the system, you should manually free the memory what you have allocated for the struct device. So that's why if you use kmalloc, then programmer must free the memory using kfree during driver detach or device detach. Sometimes programmers will forget to use kfreeze, and it may result in memory leak. That's why Linux developers have introduced the resource managed version of this kmalloc called devm kmalloc. If you use devm kmalloc, then programmers using kfree is not required. Kernel will take care of freeing memory when the device or managing driver gets removed from the system. That's why it is called resource managed API. That means this function remembers that memory is allocated on behalf of this device. There are many resource managed APIs are available. So actually you have to refer to this kernel documentation to see full list of resource managed APIs. Instead of using kmalloc and kfree, you can just use devm kmalloc. And in the GPIO subsystem, you actually acquire GPIO descriptor using GPIO dget. And if that GPIO descriptor is no longer used, then you have to deallocate that using put. So instead of calling get and put, you can just use devm underscore GPIO underscore get, like that. So some of the kernel APIs have their resource managed versions. And instead of using request IRQ and free IRQ, you can just use devm underscore request IRQ. If you use this one, then you need not to free the IRQ. It will automatically get freed. Remember that you have to use this devm versions only when you are doing something behalf of an instance of struct device. Let's see an example of devm kmalloc, which is there in driver/base/dev.res.c. Here you see these two parameters are same as kmalloc, but look at the first argument here. That's a struct device. It is like saying you are allocating this memory on behalf of this device. When the kernel detects that this device is getting removed from the system, the memory will be automatically freed. So I am in dev.res.txt in the kernel documentation. Just browse through this document. So you see list of all resource managed functions. This is for the management of clock. This is for the DMA. This is for the GPIOs, I2C. There is a devm kmalloc. There is a devm kzalloc. So for more information, you can refer to this documentation. And if we use this resource managed APIs, then we can simplify our probe and remove functions. In the probe function, what we usually do is we actually create a pointer to the device private data, and then we allocate some memory, let's say using kmalloc. After that, we check the returned pointer, and if it is null, then we return an error code saying no memory. If the memory allocation is successful, then we do something else here, and if something goes wrong here, then we jump to our error handling code where we free this. That is the previously allocated memory we actually free here. So we were doing something like this. If you introduce devm kmalloc instead of kmalloc, then you no longer have to do this. Just see here how you can simplify the probe function. So instead of kmalloc, use devm kmalloc. Here there is a failure, then you return. That's great. And after that, you try to do something. And if something goes wrong here, you just return here. Need not to use any gotos, need not to kfree, nothing. Just return. When you return an error code, so the kernel understands that the probe has failed, and it will automatically free the memory which you allocated here. That's why you can see that we can simplify the probe function by using devm underscore kmalloc. And the same thing applies to the remove function. We were doing something like this. In the remove function, we were deallocating the memory which is allocated to the buffer and the device private data. That is no longer required if you have used devm kmalloc in the probe function. That's why when you use devm kmalloc to allocate the memory in probe function, using kfree in remove function is no longer required. That's why it simplifies the remove function as well. I hope you get some idea about resource managed kernel APIs. As I said, this flavor of kernel APIs you can only use when you are doing something on behalf of an instance of struct device. Remember that. You cannot use this everywhere. It is majorly used in the probe function. And if you want full list of those APIs, you can just consult this documentation. So with that note, I would like to end this lecture. Let me know if you have any questions.
So in the previous lecture, we discussed about the dynamic memory allocation APIs, kmalloc, kzalloc, and also its resource management version like devm, kmalloc, devm, kzalloc, etc. So it's always better if you use a resource management version of the memory management APIs. In our code, we didn't do that actually. So in our code, we simply used kzalloc. It's always better if we use devm_kzalloc. That will prevent lots of code duplications. For example, in our case, you can see that in the remove function, we are writing kfreeze. Here is a code which frees the memory. Basically, you can avoid freeing of memory by yourself if you use resource management APIs. That is one of the biggest advantage of resource management APIs, so which will make your code bug free, because most of the time programmers forget to free the memories. Here we were conscious, that's why we took care of freeing of memory. But most of the time programmers, while coding, they forget to clean up the memories, and that may cause memory leak. To avoid these mistakes, the Linux kernel developers have added the resource management APIs. As I said, it also avoids code duplications. For example, here you can see that the kfree code has been used at multiple places. One, of course, in the remove function, and one more time we used the kfree, that is in the error handling of probe. Here also we have used kfree. Basically, that's a code duplication. Using kfree in the remove function can be avoided if you use resource management API for this kzalloc. Let's change this kzalloc function using its devm flavor. I'm going to modify this devm_kzalloc. So the first argument should be the pointer to the device. What I'm going to do now is I'm going to use address of pdev of dev. You can understand this code like this. This memory allocation has been done on behalf of this device, dev. When this device is going away, or when this device is getting removed from the system, the kernel will automatically deallocate the memory held by this device. That's the meaning of this code actually. Similarly, I'm going to change this kzalloc here. Let's use devm_kzalloc and the same argument pdev of dev. When the remove function gets called, and in the remove function, now you need not to do this. You can remove this because the memory deallocation will be taken care by the kernel in the correct order. You need not to worry about the order. But in the probe function, it should be there. In the probe function, you should deallocate yourself. So if the probe fails, here you can use devm kfree, devm kfree. So here you should give pointer to the dev structure. That would be fine. Let's just compile this code and let's see builds or not. Builds, no problem. Now let's add some more devices in our platform device setup file. Let me go to device setup file. Here let's create more devices. I am going to copy and paste
these structures another 2 times. This is the third device, and this will be the fourth device. First device, second device, I call it as third device, and I call this as my fourth device. And let's create different platform data. In the platform data, I'm going to remove this count here. Let's create 2 more entries. Let's copy and paste. This is 2 and this is 3. So this is the third platform data, and this is the platform data for the fourth device. I'm going to write this as 128. I'm going to select this as 32, let's say. Permission you can change here. Let me write read only. So let me make this write only. And let's change the serial number as well. We have got 4 devices. So this is the third device. This is PC dev pdata of 2. And this is 3. So now you have to call this platform register another 2 times. Now there is one shortcut. So you can use another API which is provided by the platform device.h. The API name is platform add devices. Here it is. If you use this function, then you can add multiple devices in one go. You just have to mention the count here, and you can see that it runs a loop here where it calls platform device register. But the first argument for this function is array of platform devices to add. You should create array of platform devices, and you should pass the pointer here. Let's use this function instead of platform device register. What I'm going to do is I'm going to comment this out, and I'm going to call platform add devices. For this, you have to pass array of platform devices. Let's create an array of platform devices. Struct platform device. Basically, it will be a pointer array. I call it as a platform PC devs. This is a pointer array, which is equal to. Now let's initialize this array. Here you should accumulate the addresses of all these platform devices. Let's initialize this array with addresses of the platform devices which we have created here. So the first entry would be platform PC dev 1, comma. This will be 3, this will be 4. After that, you have to pass this array to this function. This will be platform PC devs, comma, and the number of platform devices you are going to add. So you can use array size macro here. Array size of this one. By using this, you can add all the platform devices in one go. Let's test this. I'm going to do make host. Yes, it went well. And let's first remove any existing drivers. So I just run ls mode. We don't have any modules hooked. No problem. Let's do first pcd platform driver.ko. It went well. Driver loaded. insmod device setup.ko. What do you expect? 4 times the probe should be called, and we should see the information about all our devices. There is a crash. The crash says cannot create duplicate file name. Oh, alright, so I got what is the problem. Here I didn't change the IDs. So this is 0th ID, this is the ID 0, ID 1, it should be ID 2. and it should be ID3 because there was a conflict while creating the device files. Let's run ls mode to see whether the driver is really hooked up or not. Yes, it is hooked up. I think we have to remove these drivers. Let's try to remove PC dev device setup. So you cannot remove that. There is a big crash. The only resort is to reboot the machine now. Let me reboot the machine and I'll see you in the next lecture. There was a crash in the previous lecture, and as I said, that's because there was an attempt to create duplicate device files because we actually didn't change these ID numbers. Please make this change, and also in the platform exit you have to unregister 2 more devices. That we didn't do, so let's do that. 2 more times you have to call unregister, isn't it? Now let me do a make clean and let's build for the host. Let me first load the device setup code, and after that let me load the driver. Yes, here you can see that 4 devices have been detected. These are the names of the devices. So the probe was successful for every device. Let me remove the device setup code, and you can see that the device was released successfully. And now let's once again add the device setup code, and you can also see that under dev the device files have been created: PC dev 0, 1, 2 and 3, and you can use your file handling driver methods to check the data transfer between the user space and the kernel space. I hope you can test that. Try to reproduce this, and in the next lecture let's learn more about platform, device and driver matching. I'll see you in the next lecture. Hey, welcome back. In this lecture we are going to understand one more matching technique between a platform driver and a device, and the technique is using platform device IDs. First, let's understand what's the use case of this. In an embedded scenario, you generally find different versions of a chip. Let's take an example. Let's say a vendor produces temperature sensing chip. The vendor is going to produce different versions of a temperature sensing chip in their product line at different timelines. For example, let's say the vendor produces a temperature sensing chip whose name is TS-A1X. TS-A1X is the identification name of that chip, and in their product line they may also produce more advanced temperature sensing chip like B1X, C1X, like that. Such hardware spinning is common in embedded systems. So the B1X chip may be little advanced than A1X, and C1X may be more advanced than A1X and B1X. Each chip has its own configuration items or configuration parameters. So the configuration parameters or the configuration items of B1X may be a little different from configuration items of A1X. Now all these things should be handled by the platform driver. Do you think the vendor is going to give 4 or 3 different drivers to handle these 3 different families of chips? No, the vendor is going to give only one driver which is going to handle various chip families of temperature sensing chips. Generally, the vendor doesn't give you a separate driver to handle A1X family, and the vendor doesn't give you a separate driver to handle the chips of C1X family.
That means now a single driver should store different configuration items in the driver, and whenever it detects a chip, then it should verify its device ID, and then it should load appropriate configuration parameters, and thus it configures the device properly. That means now the platform driver must support different device IDs to compare. In this hypothetical example, the platform driver must support 3 different IDs like TS, A1X, B1X, C1X. When it detects a platform device whose name matches with any of these entries, then that's a matched device, and the probe function will get called, and it can then configure that device. For this use case, the driver uses something called device IDs. We are going to support this matching feature to our driver now. You have to now modify the PCD platform driver to support different versions of PCDevs. So now what we'll do is we will give a unique ID to every device. Like I would like to call the first device as PCDev A1X, PCDev B1X, and PCDev C1X. And then we are going to maintain the supported ID list in the driver, and then we are going to configure them appropriately. So now let's again explore our platform driver structure. Here you see platform device ID. So here you should hook up your ID table, that is device ID table. If you just explore this structure, this is a very simple structure which is there in mod_device table.h. It's a very simple structure which consists of only 2 member elements. The first one is a name. Here you are going to save the device ID name which your driver is going to support. And this field is a long integer type which is used to hook up the driver data. So we'll see the use case when we code for this in our driver. Let's get into our code, and let's first open device setup.c. Here we are going to support 4 devices, but the name is different now. This device name is PCDev A1X, and this device name is PCDev B1X. And this is C1X, and the rest of the code will be same, no changes here. I'm going to exit. Let's open driver code. Here now it is not a simple name based matching. Now we are going to use the ID table matching. This name matching will not be carried out now. This becomes now redundant. Let's go back, and in the platform driver structure, let's initialize this field. But before that, we have to create this structure. Let's create that. Here, let's create struct platform device ID. Platform device ID. It should be an array, remember. Why? Because you are storing multiple names. That's why it should be array. I would call it as PCDevs IDs is equal to, let's initialize the first array element. I'm going to initialize now is equal to dot. So what's the member element name? Name dot name is equal to, I would call it as PCDev A1X. And after that you have to initialize this driver data, but for a time being I'm not going to use that field. In the next lecture, let's understand what's the purpose of that field. I'm just leave it here. Yes, that's over. Just close the bracket, and let's go for the second array element initialization, that is 1 is equal to, or let me just copy paste this 4 times. This is 1, this is 2, so not 4 times, I'm just going to use 3 times. 0, 1, 2, this is B1X, and this is C1X. This driver doesn't support D1X. That looks fine. So now what you do is just use this field ID table. ID table is equal to, just use this pointer. By using this table, in this driver you have given a support for the device whose name is either A1X or B1X or C1X. When you use the ID table entry here, then this name will no longer be used for device and driver matching. This you can verify by using the source code of platform match. Let me take you to the implementation of where the matching happens in the Linux kernel source. That actually happens in the function platform match. I think you should go into drivers, base, platform.c. Here just search for platform match. So here it is. Bind platform device to platform driver. You see here different types of matching. A matching between device and driver happens here. First, this function, it tries to match using OF style. That is something to do with device tree related matching. Then it tries for, if that is successful, it returns here. You can see that. It doesn't care about other type of matching. And then it tries for ACPI style match. And then it comes to the ID table match. So if the ID table match is successful, then it returns here. It doesn't care about the last result, that is the driver name based matching. You can see that it's a simple string copy. Your PDAV name is compared with driver name. So far, what was happening in our case was this final result. Everything was failing here, and the matching function, lastly, it was verifying the driver name and the device name. So now it won't happen because we have initialized the ID table. That's why it will go into the platform match ID function. Here it is, where it runs a while loop and it checks your list, what you have provided. Let's get back to the code, and I think everything is fine. Let's just try to build the code. There seems to be a lot of error. I think you should include header for this. It is defined in mod device table.h. Let's copy this name. Let me add that header. Yes, the build was successful. And first remove the loaded drivers, if any. So let me check using ls mode. There is one driver is already hooked up. Let me remove that first. Let me just clear the D message. First, let me load the device setup. Device setup module loaded, and now let me load pcd platform driver.ko. Here it is. You can see that it detected 3 devices. For the fourth one, it was not successful because it was D1X. That support we have not given in our driver. That's about device ID matching. And suppose in the driver, if you want to support a D1X, then you can create one more entry here. You can mention that device ID. And let's first remove the platform driver. Need not to remove the device setup. Just load again. So you can see that now all 4 devices have been detected. That's about the use case of platform device IDs. And now let's get back to this structure platform device ID. Now you may be wondering what is the use of this field driver data. Who is going to use this structure? This structure is going to be created by the driver. That means driver is going to set this field, driver data. In this field, the driver is going to store some configuration data related to that device, so that when the device is detected and when the probe is called, the driver can extract that data in the probe function, and then it can configure that device using that configuration data. Because I said in the previous slide that every device will have its own configuration items to configure. That is generally the case in hardware programming. These configuration items are not provided by the platform. These are maintained inside the driver. The driver maintains that in this field, driver data. So when the device is detected, it can extract that data back. Let's see how to use this field. For that, I'm going to my driver code. Here, let's create some dummy configuration structure, something like that. What I do here is I create some device config structure. Let's say this structure has a couple of member elements. Let's say int config item 1, int config item 2, something like that. Here we are supporting 4 devices. Let's create an array of this structure type. Struct device config pc dev config is equal to the first device config items will be, let's say, config item 1 is equal to, let's say, 60, and second config item will be, let's say, 21. And this is for the next device. Like that, I'm going to copy this. Let me make it as 50, 40, 30. So this would be 22, 23, 24, something like that. This line signifies that this is a configuration item must be used to configure PC dev A1X device. When this device is detected, the driver should use this one. Now the question is, so in the probe function, how does the driver is going to extract this information when this device is detected? For that, the driver data field is used. You can make use of this driver data field. What you do is, let's initialize the driver data field. Here you store, this is actually a long data type. So here you store the ID of this configuration item. The ID is 0, so you can store that here. Like you can store 0 here. When the probe function gets called, so from the platform device structure, you can extract this driver data portion, and by using this ID, you can get the configuration item, and then you can configure the device. In order to make this intuitive, let's do one more setting here. I'm going to use enum to give a special name for these IDs. What I'm going to do is enum PC dev IDs or PC dev names. I'm going to maintain some names here. PC dev A1X, PC dev B1X, PC dev C1X, and PC dev D1X. So in an enum, the value for this will be 0. If it is not initialized, then this will be 1, this will be 2, and this will be 3. Instead of using 0, 1, 2, 3 here, I'm going to use enum values. PC dev A1X, and this is PC dev D1X. So this is more intuitive than the earlier method. You can easily make out that this is a configuration item which belongs to PC dev A1X. Here there is a problem. This is device config. Sorry about that. Config. And here this comma is not required. Let's terminate this structure here. In the driver data, you can simply give PC dev A1X here. Similarly, initialize the driver data for the next one. Please note that I'm just storing a number here. This is not an address, so this is a number. So let's try to build. The build is fine. Let's go back to the probe function. When the probe function gets called, so you have a pointer to the matched platform device. That is matched platform device. Where is the platform device? Here is the platform device. You have a pointer to the matched platform device. And matched platform device ID pointer will be in this pointer variable. So you have to consult this pointer variable to extract that driver data. In the probe function, I'm going to print back those config items. Maybe here. What I do is, let's print pr_info config item 1 is equal to %d. How do you extract the config item? So you should consult this array. That's why what we'll do is, let's keep all these things at the beginning of the driver. I'm going to cut all this code. Let's put that in the beginning, maybe here. That looks good. The probe function has to consult this pcdev_config. pcdev_config of pdev, dereference that, select id entry, dereference that, and select driver data, because that's the index. pcdev_config of this element dot config item 1. That's how you extract the config item 1. Similarly, let's print the config item 2. So now let's check this code. Everything is fine. Let's remove already loaded drivers. insmod pc device setup.ko, insmod pcd platform driver. Here it is. This is the first detected device, and these are the platform data, and this is the configuration data of this device, which the driver extracted using the driver data field. You can see that every time it is different. That's about the ID table matching, and there is one more method we need to explore, that is device tree matching. So that we can only explore after completing the basics of device tree writing. That's about the basics of platform device and a platform driver. So don't worry, we'll do more exercises as we move along with this course. Before ending this session, I would like to cover one more important thing while writing the platform driver. In this driver, we used the module init function, a cleanup function, and after that we used these registration macros. While writing a platform driver, all these things can be replaced by a single macro called module platform driver. Basically, this macro inserts these init and cleanup functions. Actually, this module later expands to these init and cleanup functions and these module registration macros. So this macro is defined in a platform_device.h, where it says it's a helper macro for drivers that don't do anything special in module init and exit. This eliminates a lot of boilerplate codes. Each module may only use this macro once, and calling it replaces module init and module exit. Please note that, so if your job in the init and cleanup function is just to register a platform driver and to unregister a platform driver, then only you can replace these functions with this macro. Otherwise, you cannot use this macro. For example, in our code, apart from calling platform driver register and platform driver unregister, we did several other things such as alloc chardev region, unregister chardev region, a class creation, etc. We included those codes in the init and exit macros. That's why I didn't use this macro. You can use this macro only when this init and exit function consists of platform driver register and platform driver unregister. If that was the case, then in your platform driver, you can replace this init and exit with module platform driver, and you just have to mention this platform driver name. This much is sufficient. You need not to write init, you need not to write cleanup, you need not to call platform driver register, you need not to call platform driver register or unregister. Everything will be taken care by this single macro. But as I said, we cannot use this macro because we are implementing some other functionalities in the driver init and cleanup other than just registering and unregistering. So this macro is actually defined in platform device.h, and if you just see this macro module platform driver, it then calls this module driver macro. This module driver is actually implemented in device.h. So here you can see that helper macro for drivers that don't do anything special in module init and exit. And here you can see that this macro implements the init and exit function for you. And it also includes the platform register and unregister code here. So with that note, I would like to end this lectures on platform device and drivers. So we'll see more exercises as we make a progress in this course. And from the next lecture onwards, let's explore about device trees. I'll see you in the next lecture.
Hey, welcome back to the lecture. In the previous lecture, I actually said that when you use resource managed APIs such as devm_kzalloc, so what I said was in the pro function you have to use devm_kfree to release it manually, but that is actually not true, because I was going through the code and I found something which I would like to share. Actually, your pro function, the pro function of the driver will get called by the function called really probe, which is there in dd.c, base dd.c. You have to go to Linux drivers and go to base. Here you see dd.c, here it is, and here search for really probe. From this function, the probe function of your driver gets called. You can see that here. Let me maximize this. So you can see here driver probe. It calls the driver's probe method here. If the return value is non-zero, and it jumps to the probe failed, which is right here, probe failed. And you see here dev res release all. This function releases all the resources held by struct device. That's why if probe fails, the memory which is held by that device will be freed automatically. Let's go to this function dev res release all. release all managed resources. This executes and your memory will be released. That's why I would like to make a correction now. So this buffer free is not required. Let's remove that. We can make this error handling pretty much simple. I will show you. Now this go to cdev delete is not required. So I'll remove this jump. I will just cut this code from here and I will paste here. If the device create fails, then get the error code in RET, delete the cdev and just return. So that's why let me remove this cdev delete and let me remove this print statement also, and let's remove this as well. I just removed everything. Let's go here and instead of this go to out, let's just return here itself. After that, so here also just remove that and just return enomam, and after that here as well. So here also just return. Just remove this cdev add, and if return is less than 0, then just print cdev add failed and return. Yes, now it looks simple, isn't it? You can keep one print statement here. Instead of a PR info, you can also use dev info. That would be better for resource managed printing. But for the time being, let's stick to a PR underscore info. So here you can print probe was successful and just return 0. And if there is any error in between, then the code will return that itself. That's why need not to separately implement the error handling at the bottom. So in this section, let's understand